Imagine an AI agent, right? And it successfully writes this complex, totally bug-free web application for you.
Sounds great.
Yeah, it's amazing. I mean, it navigated the documentation, it spun up the server, wrote the front end, and even debugged the database connections.
Right.
But, and here's the catch, when you look under the hood and ask the model which specific line of code or like which terminal command actually solved the core bottleneck, it basically just shrugs.
Yeah, it has absolutely no idea.
Exactly. And that is the bizarre paradox of modern AI agents. They are, incredibly smart at generating these massive multi-step behaviors, but when it comes to figuring out exactly which of their actions actually led to their success or failure, they are often just completely in the dark.
It's the classic black box problem, really,
Yeah.
but elevated to a behavioral level.
Oh, for sure.
I mean, the model knows it crossed the finish line, and it knows it got a reward for doing so.
Uh-huh.
But it has a profoundly hard time pointing to the specific, steering maneuver that kept the car on the track.
And that bottleneck is the exact paradox we are unpacking for you today. Welcome to the deep dive. We are looking at a brilliant new paper titled, let me get the full name here, AEM, Adaptive Entropy Modulation for Multi-Turn Agentic Reinforcement Learning.
It's a bit of a mouthful, but it's a great picture.
It really is. And the mission for this deep dive is to explore how two researchers built this incredibly elegant, totally supervision-free solution to help AI agents learn more effectively.
Yeah.
And honestly, the wildest part is how they do it. They basically teach the model to listen to its own internal sense of mathematical surprise.
Which is just a fascinating approach.
Okay, let's unpack this, because before we get to the AEM solution, we really need to understand the exact roadblock these researchers are trying to bypass, right? Because training an agent to do 50 things in a row is vastly different than training it to just, answer a single question.
Absolutely. And if we connect this to the bigger picture, the core issue here is something called the sparse outcome-only rewards in agentic reinforcement learning.
Right.
Picture a large language model agent interacting with an environment like a simulated web browser. It has to click a search bar, type a query, scroll through the results, find a specific link, click it, and finally hit a buy button.
That's a lot of steps.
Exactly.
Yeah.
That could easily be 30 consecutive distinct actions. But the environment is silent the entire time. It does not tell the agent if it's doing a good job along the way.
Yeah.
It only delivers the reward at the very, very end of the entire sequence.
So it gets a 10 for success if it finally bought the right item, or a 0 for failure if it bought the wrong thing.
Right.
Or, maybe it just got stuck in an infinite loop scrolling on a Wikipedia page somewhere.
Yeah, that happens a lot.
And that creates a massive credit assignment problem. It actually makes me think of like a basketball team making 20 complex rapid-fire passes before finally taking a shot at the buzzer.
Oh, that's a good way to look at it.
Right, because if the shot misses and the buzzer sounds, the whole team gets penalized, everyone gets blamed. If the shot goes in, everyone gets praised.
Right, everyone gets the same reward.
Yeah. But what if 19 of those passes were just terrible, highly dangerous ideas, and the final player just made a miraculous lucky shot? The players who made the terrible passes suddenly receive a positive learning signal for a really bad action.
Exactly. To take your analogy further, those exploratory, decisive, and redundant steps are all receiving the exact same indistinguishable updates.
Yeah.
And this completely obscures the distinction between a confident, correct move and a highly uncertain, lucky guess. Ultimately, that noise, it just severely limits how efficiently the AI can learn to navigate complex environments.
Right, and I imagine the knee-jerk reaction from the industry was just to throw more human data at the problem, like grade every single pass on the basketball court.
Yeah, that was the initial instinct for sure.
We see that with process reward models, where you basically hire an external coach to grade every single micro-step, but paying experts to annotate thousands of trajectories and then, training a separate model just to deliver those grades.
It feels completely unscalable.
Right, and then you have researchers trying to build self-supervised methods to avoid needing human graders altogether. But my understanding is those approaches come with their own massive flaws.
They do, unfortunately. Some self-supervised methods try to solve this by grouping similar outcomes together, but they end up suffering from what we call grouping bias.
Okay, what does that mean in practice?
Well, they might accidentally penalize a brilliant, highly unique action just because it doesn't look like the rest of the group.
Oh, interesting.
Yeah. And then you have tree-structured optimization methods, which basically force the model to build out massive branching paths of all possible actions to see what works best.
Which sounds expensive.
It is incredibly computationally heavy. They will completely melt a GPU cluster. So we really need a fine-grained credit assignment framework that doesn't need hand-holding or restrictive structural assumptions.
And that is exactly where the authors of the AEM paper looked inward. Instead of building an external grading system, they looked at the policy's own entropy, basically the model's internal uncertainty. But here is where the paper does something really interesting. They argue that we've actually been measuring entropy at the completely wrong scale. They initiate a critical shift from token-level entropy to response-level entropy.
This is the crucial pivot in their research.
Now, wait, you're losing me a bit here. As an AI researcher myself, I got to push back. We have spent the entire deep learning boom optimizing token-by-token generation. Large language models are, at their core, next token predictors.
Right, that's what they do.
Why throw that granularity away for this response level approach? Why is token level suddenly the wrong granularity for this?
Well, what's fascinating here is the perspective of the environment itself. In traditional LLM training, we do look at the uncertainty of every single token, every letter, every space, every comma.
Sure.
But in agentic reinforcement learning, the environment does not react to a single token. It reacts to a complete response.
Okay, I see where this is going. The simulated web browser doesn't care if the model predicts letter C, then L, then I, then C, then K. It only updates its state when the full command string, like click the search button, is finally executed.
Precisely. The response is the effective interaction unit because it combines the model's internal reasoning with its external action. And the authors actually proved this mathematically in theorem 3.2.1 of the paper.
Oh, wow.
Yeah, by elevating the entropy analysis to the response level, they achieve a structurally faithful measure of uncertainty that mitigates the massive sampling noise you get at the token level.
Okay, let me make sure I'm visualizing this grammar noise correctly.
Right.
A model might be highly uncertain about whether to use a comma or a semicolon in its internal thought process.
Right.
Which creates a huge mathematical spike in its token-level entropy. But it might be 100% certain about the actual action it's going to take next.
Exactly.
So if we only look at tokens, we get distracted by that useless grammatical spike. By zooming out to the response level, we get a much clearer, more reliable signal of the model's true confidence in its decision.
You nailed it. And once you establish that clear, reliable signal, you can actually use it to modulate the training updates. This brings us to the core mechanism of the paper, relative response surprisal.
Okay, here's where it gets really interesting. So we have this beautiful response level uncertainty score. My intuition says we should just penalize the model whenever it's uncertain, to force it to be more confident.
A lot of people might think that.
But that would completely kill its ability to explore, wouldn't it? So how does AEM actually use this surprisal metric?
Yeah, penalizing uncertainty across the board is exactly what causes models to get stuck. Instead, AEM, which stands for Adaptive Entropy Modulation, acts as a mathematical plugin that dynamically adjusts the advantage of a step.
The advantage being the score indicating whether a specific action was better or worse than the baseline average?
Exactly. AEM modulates that score using a proxy for how surprised the model was by its own response.
Let's walk through what that looks like under the hood. For you listening, how does the math actually work out?
Let's say the prompt generates 8 different possible responses. AEM calculates the response level entropy for each one, finds the baseline average across that specific batch, and then it creates a specific ratio, which they call the alpha coefficient.
Okay, the alpha coefficient.
Right. Alpha directly compares the surprisal of a specific response to the baseline of that whole group.
So instead of just relying on the final outcome score, that sparse 10 or 0 at the end of the run,
Yeah.
the model is essentially grading itself on a curve based on its own internal confidence.
Yes, and the math dictates exactly how the update is applied. If the alpha ratio is greater than 1, it means that specific response was less surprising to the model compared to the group average. It was a highly confident move.
Okay.
In that scenario, AEM upweights the advantage.
And I guess the flip side of that, if alpha is less than 1, the response was more surprising. It was kind of a shot in the dark. So if the agent suddenly succeeds using a move it was highly uncertain about, AEM's math steps in and amplifies the positive signal. It essentially tells the model, hey, pay close attention to that. We didn't expect that to work, but it did. We need to learn heavily from that unexpected success.
That's spot on. And the inverse is equally powerful for failures. If the agent was highly confident in a move, meaning it was completely unsurprised by its own choice, but that move led to a massive failure.
Ouch.
Yeah, AEM amplifies the negative signal to aggressively correct that false confidence. The authors establish in Theorem 3.2.2 that the local entropy drift during training is governed intrinsically by this dynamic.
Wait, local entropy drift? You mean the natural tendency for a model's overall uncertainty to fluctuate as it updates its weights over thousands of training steps?
That is the perfect way to frame it.
Yeah.
Entropy drift is no longer random or tied to manual schedules. It is governed intrinsically by the mathematical product of the advantage, was the outcome ultimately good or bad, and this relative response surprisal. It literally multiplies the external result by the internal surprise to determine the magnitude of the learning update.
That is incredibly elegant. But, I mean, as anyone who has ever trained a reinforcement learning model knows, just tweaking the advantages for a single step is only half the battle.
Oh, absolutely.
You have to string tens of thousands of these updates together over a massive training run. And that leads to one of the biggest headaches in AI training, balancing exploration and exploitation.
It's a huge challenge.
Yeah.
Because it raises an important question. How do you get an agent to explore wide-ranging possibilities when it is performing poorly, but narrow its focus and stick to the winning strategy once it actually gets good?
Because if it just exploits its existing knowledge too early, it might get stuck doing something suboptimal forever.
Right.
But if it never stops exploring, it never perfects a winning strategy. And usually we have to meticulously hard-code learning rate decays, or we have to manually tune these complex, handcrafted entropy penalty schedules to force that transition.
It is a nightmare of hyperparameter tuning.
Hold on, are you saying AEM just handles this transition on autopilot?
I am. It facilitates an implicit, fully self-adaptive transition, and the mechanics behind it are just brilliant. Picture the early stages of training an agent on a complex, multi-step task.
It's basically a toddler randomly slamming a keyboard. Almost all of its responses are going to fail.
Exactly. And because of that high failure rate, the training batches are heavily populated with negative advantages. Under these specific mathematical conditions, AEM naturally applies what we call entropy increasing pressure.
Okay.
Since the model is consistently failing using moves it originally thought were good, AEM forces the model's overall entropy up. This actively prevents the model from prematurely collapsing on a bad strategy. It literally forces the agent to keep its options open and aggressively explore the state space.
Okay, so it protects the model from getting overconfident in its own bad ideas. But what happens when the agent actually starts learning and getting things right?
Well, as the success rate inevitably rises, the training batches begin to contain more and more positive samples. The environment is returning more successes and fewer failures. And AEM adapts to this new balance entirely on its own.
That's amazing.
The math naturally shifts, and it begins to apply entropy decreasing pressure.
Because now the agent is succeeding using moves it is mathematically confident in. So AEM is narrowing the focus and locking in the winning behavior.
Exactly. The paper provides a fantastic analysis, showing that while standard baselines, like regular GRPO, often suffer from premature entropy collapse.
Where they just latch onto a mediocre, safe strategy early on and completely flatline.
Exactly. While baselines do that, AEM smoothly transitions into exploitation mode. It preserves response diversity early on, and then converges on high-quality solutions later, entirely driven by the evolving balance of positive and negative samples. No manual tuning required.
Okay, the results are what I want to see. But if you've ever trained an RL model, you're probably wondering how AEM handles all the sophisticated math across entire response groups without completely melting your GPU.
Oh, for sure.
Before you give me the success rates, tell me the bad news. What is this going to cost my GPU cluster? Usually, when you introduce fine-grained credit assignment methods, the compute overhead is the catch that makes it unviable for production.
Get ready for the most impressive part of the paper.
Okay.
The computational overhead is, well, it's essentially zero.
Wait, really?
Really. Technically, the authors report that AEM accounts for exactly 1.1% of the training step time. In their specific hardware breakdown, the AEM calculations took 5.62 seconds out of a 500-second training step.
I am genuinely struggling to understand how that is possible. If it's analyzing the entropy of an entire group of complex responses, generating averages and applying ratios, how is that not adding massive compute time?
Because AEM does not require any extra rollouts, and it does not require any additional model forward passes. The brilliance is in the reuse of data.
Oh, I see.
It simply takes the log probabilities that the standard training loop is already calculating anyway. It takes that existing data, applies its length-normalized entropy proxy math to calculate the alpha coefficient, and rescales the advantages. It operates entirely on the back end of the existing forward pass.
That is software engineering at its finest. Maximum signal extraction with zero extra generation cost. But, okay, a beautiful mathematical theory and lightweight engineering are great. But as practitioners, we only care if the numbers go up on the leaderboards. What environments did they actually test this in?
They tested AEM across models ranging from 1.5 billion parameters all the way up to 32 billion parameters. And they ran them through 3 brutal multi-turn agent benchmarks. ALF World, Web Shop, and SWE-bench-Verified.
Let's break those down for the listener. ALF World is the household text-based environment, right? Things like navigating a simulated kitchen to find a key or heat an apple in a microwave. And Web Shop is the massive simulated e-commerce environment.
And Web Shop is incredibly complex. It has over 1 million simulated products. The agent has to navigate HTML, use search bars, parse product attributes, and click to buy specific items based on highly detailed natural language instructions. When they applied AEM to a relatively small 1.5 billion parameter Quinn model using the GRPO baseline, they saw a peak gain of plus 8.8% on ALF World and a plus 5.6% jump on Web Shop.
Wow. Nearly a 9% absolute gain on a multi-step reasoning task just by swapping how you handle the internal credit assignment with basically no extra compute. That alone proves the methodology. But I want to talk about the heavyweight benchmark, SWE-bench-Verified.
This is where AEM really proves its worth in the real world. SWE-bench-Verified is a highly curated subset of real-world software engineering issues pulled directly from GitHub.
Oh, boy.
The agent is given a bug report. It has to independently navigate the code repository, grep for relevant files, edit the code, run tests, and verify the fix. It requires incredibly deep, long-horizon reasoning.
It is notoriously difficult for an agent to stay on track over 50 or 60 terminal commands in a sprawling code base.
Absolutely. So they integrated AEM into DeepSWE, which is already a state-of-the-art reinforcement learning framework running on a massive 32 billion parameter model. Integrating AEM bumped the absolute success rate up by a clean plus 1.4%.
I want to pause on that because a 1.4% gain might sound small to someone outside the field, but we are talking about a 32 billion parameter model on an already highly optimized baseline and one of the most punishing coding benchmarks in existence.
Exactly.
Eking out even a single percentage point at that scale requires fundamentally better reasoning. It means the model is solving highly complex, previously unsolvable bugs simply because it finally understands which of its terminal commands are actually driving the solution.
It firmly establishes that entropy-aware response-level credit shaping is an incredibly effective inductive bias. It scales effortlessly from a 1.5 billion parameter toy model, navigating a simulated kitchen, all the way to a production-level 32 billion parameter framework editing real-world Python code.
So what does this all mean for you listening? Let's synthesize the journey we just went on. We started with this persistent, frustrating problem. AI agents lost in a sea of complex multi-step tasks, receiving only a single sparse reward at the end and having no idea which of their actions actually mattered. It was the basketball team praising a terrible pass just because someone else hit a miraculous buzzer beater.
And we examined how relying on external human grading is financially unscalable and how traditional token-level analysis gets distracted by the grammar noise. The environment reacts to the full executed action, not the individual characters being generated.
Adding to that, we explored the genius of AEM's mathematical shift to response-level entropy. It empowers the model to calculate its own relative response surprisal. It uses its own internal surprise to grade itself on a curve, dynamically modulating the learning signal so it actually pays attention to its unexpected successes and harshly corrects its confident failures.
And moving beyond just the individual steps, we saw how that simple mathematical shift puts the macro transition from exploration to exploitation on autopilot.
Early on, the negative advantages create entropy-increasing pressure, forcing the agent to keep exploring wide-ranging strategies. As successes mount, the math naturally reverses course, narrowing in on the winning strategies and avoiding the trap of premature entropy collapse.
And all of this happens for practically zero compute cost by ingeniously reusing existing log probabilities. And it's proven out on benchmarks ranging from simulated online shopping to resolving real-world GitHub issues. It is an elegant, highly scalable solution to one of the thorniest problems in agentic reinforcement learning.
It really is a paradigm shift for training. But if we pull back even further, this methodology raises a profound question that goes beyond just the training phase.
Oh, What's that?
Well, if an AI can use its own intrinsic surprise to autonomously balance exploration and exploitation, while it learns what happens when we start using that exact same internal uncertainty metric during live, real-world deployment.
Oh, that is a fascinating angle. Could an agent, operating autonomously in the wild, calculate its own relative response surprisal in real time? Could it realize that it is too surprised by a complex coding task or an unfamiliar web interface?
Yeah.
And instead of just guessing, executing a highly uncertain action and potentially breaking a production server, could it automatically know exactly when to pause, halt its actions, and ping a human for help?
That is an incredible thought to leave on. The idea that a model's mathematical internal surprise could not only be the secret to better training, but the key to safe, autonomous AI deployment in the real world. Thank you for joining us on this deep dive. Keep questioning the black boxes, keep exploring